The other day, the amateur cosmology group that I go to had a lecture on asteroid occultations, and as part of that lecture we were given these questions to try to answer. So shout out to Wim Noble of the Asteroid working group who gave the lecture. I'll link to the group's website in the video description. Okay, I answered these questions using Fermi approximations with a pen and paper during the lecture, and after the lecture I got a couple of requests to do a video explaining the techniques that I used. I will include timestamps in the video description, so anybody who wants to skip the explanation of what a Fermi approximation is can do so. Fermi was famous for asking what other people would think of as bizarre job interview questions. If you applied for a job with him, you might be asked something like, how many piano tuners are there in Manchester? And if you said, I don't know, but I'll look it up, then you would not have got the job. Instead, you were expected to do an order of magnitude calculation by thinking on your feet. The key to this is to begin by making an assumption that there are not likely to be many more piano tuners than the city can support, or far fewer for that matter. So typically, you might start by guessing that the population of Manchester is probably more than 100,000. It's also probably less than 10 million. So to the nearest order of magnitude, there are population Manchester approximately 1 million. My handwriting is appalling, by the way, and also I can't spell because I'm dyslexic, so apologies for all of that. So you might then guess that the average household size is 4. It's probably wrong. The real answer is likely to be more than 1, less than 10. So 4 is probably good enough. The technique does not require that every number is an order of magnitude. One thing that you would normally do is you would, as you're going on, you would think, okay, I guess that number too big, so the next number I should guess too small. So, like, let's say you think one number should be somewhere around 2.3, but 2.3 is too much accuracy. So you say, okay, it's 2. And then the next number you might think is, maybe about 9, and you're happy guessing 10. But all of the time, what you're really doing is you are trading accuracy that you don't need for time that you do, because you could do other things with the time. So, okay, so household size approximately 4. So that gives us households in Manchester approximately 250,000. Okay, So next, we might guess that roughly 1 in 100 have pianos. So percentage with pianos, 1%. So therefore, pianos in Manchester approximately 2,500. So the next question is, how often does a piano need to be tuned? And it depends how much it's being used. I think, like, a lot of people would tell me that saying only 1% of households have a piano is too small. A lot of people would say maybe a piano needs to be tuned once a year. I kind of think that nowadays fewer people have pianos, but the ones who do have them probably use them a lot. Because if you've got a piano, you probably care nowadays. So I'm going to say maybe you tune it once a month, which means 10 tunings per year. Obviously it means 12, but it's a Fermi approximation, so we're going to say 10. So 10 tuning events per piano per year. So 25,000 tuning events. Fine. So how many tuning events does a piano tuner make in a year? One kind of typical approximation I work with is that any kind of freelancer, and they're almost certainly freelancers, works about 200 days a year. Work days per year, 200. And let's say they're pretty busy, so they tune 5 pianos a day. So times 5 pianos per day equals 1,000 piano tuning events per tuner per year. So since there are approximately 25,000 required tuning events, and each piano tuner can make 1,000 of them in a year, that means answer approximately 25 tuners. Okay, so the point of a Fermi approximation is not to get the exact answer. The point is to get within an order of magnitude, exactly how much accuracy you need depends on the problem, but typically you say if you're within an order of magnitude, you consider that a win. So is this within an order of magnitude? Well, what we're saying is that there are between 2.5 and 250 piano tuners in Manchester. And I don't know the right answer, but I would say, yeah, there's probably a very good chance that the 25 is within an order of magnitude. Okay, so if you were able to do that during a job interview with Fermi, then you would have been on your way to getting some work with them. So here's the challenge. We're going to do a similar exercise to answer Wim's questions using just pen and paper and the knowledge we have in our heads. But first of all, I've got to make some notes about the question. So this symbol here means diameter. The question has been translated from Dutch, and there are a couple of things that the translation software missed. AE in Dutch stands for Astronomische Eenheid, which means astronomical unit in English. So in English we would put AU instead of AE. And I'm sure that most people watching this video would know, but AU is the distance between the Earth and the Sun, approximately. Yeah. It has an exact definition nowadays because we know it's getting slightly bigger each year. So, but yeah, it's the distance between the Earth and the Sun. Okay, LJ stands for Lichtjahr, which is light year in English, so we would write LY. The asteroid is fictitious in the picture, so is the star, which is a segue into the next thing that I wanted to talk about, which is unless somebody specifically asks for an approximation, you don't necessarily know, but it's kind of obvious from this question that an approximation is going to give us a good enough answer for two reasons. So the first reason is that a lot of the data we've been given has been given to us to what is apparently a very low precision. The diameter of the asteroid and the star are only known to one order of magnitude. The distance of the star is given as 100 light years, not, for example, 103.8. The only figure that we have, which isn't an order of magnitude figure, is the distance to the asteroid, which is given as 3 astronomical units. That's still a very low precision. So maybe the asteroid is precisely 3 astronomical units away, but it seems more likely that the question does not give us precise values because a precise answer is not required. There is also a kind of rule or convention that you wouldn't normally give an answer with accuracy that isn't justified. So if you're using a whole bunch of figures where the accuracy of the figure is not specified to more than, say, 3 decimal places, then when you give your answer, you would not give your answer to 4 decimal places because you can't justify the 4th decimal place based on the data that you've got. Similarly, normally, if you have a figure of, let's say, let's say the diameter of the star. So if the diameter of the star is given as 1 million kilometers, maybe it is exactly 1 million kilometers and not 1,000,001 kilometers. But normally, if it was precisely 1 million kilometers, you wouldn't write it like this. You would write either 1,000,000,000, or more likely you would write 1.00000 million kilometers. That way people know that you are declaring the precision. And since none of that has been done in this question, we can assume that this is something that we have approximate questions, and therefore we can give an approximate answer. Okay, the second reason is that there is a lot of information that we would need in order to make a precise calculation that's missing from the question. We don't know the shape of the asteroid. The picture is just for illustrative purposes. And in fact, the reason that Wim's group observe occultations is to try to figure out the shape of the asteroid. So we know that the picture is not the actual asteroid, and it's clear from this that the diameter that we have been given is just an estimate of the average diameter. This means that the direction that the asteroid is in when it passes in front of the star will significantly alter the length of the transit. Obviously, if it is moving this way, the occultation is going to be a lot longer than if it is moving this way. Another thing we don't know is where the Earth is in relation to the Sun and the asteroid. It might make sense for the Earth to be on the same side of the Sun as the asteroid. Normally, when you want to do observations, it's nice to be as close as possible. But you can't guarantee that. And there will be cases where an occultation is going to happen, and the time that the occultation is happening, the Earth is off to one side. If you only did these observations when the Earth and the asteroid lined up perfectly, then you wouldn't be able to make very many observations. If the Earth is behind the Sun, that's kind of unlikely, because then the Sun's in the way, and obviously we have to make the observation at night. But it is possible, because, you know, orbits are in 3 dimensions, not 2. Because it's going to simplify the question, I'm going to assume that for most of the calculations that I make, I'm going to assume that the Earth and the Sun are in the same place, which works for a Fermi approximation. I'll cover potential issues later in the video, but my point is that if we were being asked to make an accurate calculation, we would have to know where the Earth is in relation to the Sun and the asteroid. So, the last thing I need to address before I start is that on the face of it, it looks like we have to do trigonometry with just pen and paper in order to do this challenge. That's technically true, but there are a couple of tricks that you can use to make it possible to do this. They only work for small angles, which is great for astronomy. These tricks almost always work because in astronomy, almost all angles are small that you need to measure. If you're measuring the angular diameter of something, then it's probably going to be very small. The only exception I can think of is a nearby galaxy, like the Andromeda or something, which I think is somewhere around 3 or 4 degrees across. Even 3 or 4 degrees is probably small enough for these approximations to work. I might be wrong, it might be bigger, but I've got a feeling it's something like 3 or 4. Anyway, okay. So, for example, it's a well-known fact that the Sun has an angular diameter of about half a degree. The trick is, when angles are small, the angular diameter is proportional to the diameter, the actual diameter, and inversely proportional to its distance. So a slight diversion into the units that you use for small angles. For angles that are smaller than 1 degree, there are other units that we can use. Arc minutes, arc seconds, and for really small angles, milliarc seconds. So 1 degree is 60 arc minutes, 1 arc minute is 60 arc seconds, 1 arc second is 1000 milliarc seconds. So, let me start a fresh page. Okay. So the Sun is half a degree. Which is 30 arc minutes. I believe, from memory, it's actually sort of closer to 31. I might be wrong, but 30 is fine anyway. So returning to the explanation of the trick. An object with the same diameter as the Sun, but so if the Sun was 10 AU away instead of 1 AU away, then its angular diameter would be 3 arc minutes instead of 30. So, like I said, inversely proportional to the distance. So you multiply the distance by 10, you divide the angular diameter by 10. Then let's say we double the diameter of the Sun. So if you double the diameter, then you get 6 arc minutes. There is some complexity behind why this trick works for small angles but not for large ones. But explaining it is really the job for a separate video, because yeah, this video is going to be long enough as it is. Okay, fine. So finally, we can address the problem itself. So we're going to use the fact that we know that the angular diameter of the Sun is about half a degree, and we know that it's 1 AU distance. So from memory, the Sun is roughly 1.4 million kilometers in diameter. Because this is a Fermi estimate, I'm going to pretend that the Sun is the same size as the star. I'm going to say it's not 1.4, it's 1 million kilometers in diameter. So, we're going to start with the asteroid. The asteroid is 3 AU away and the Sun is 1 AU away, so we need to divide the Sun's angular diameter by 3. So we start with 30 arc min, and we are dividing by 3 because it's 3 AU, not 1. So that gives us 10 AU as the angular diameter that the Sun would have if it was that distance away. So now we need to reduce the angular diameter again. For the difference between the actual diameters. So 10 we need to multiply by the actual diameter of the asteroid, which is 100 kilometers, and we are going to divide by 1 million kilometers because that is our pretend angular diameter for the Sun. So, okay, so this is 1,000 on the top, 1 million at the bottom. That cancels out to 1,000, 1,000th of an arc minute. Now, I'm going to use milliarc seconds because it, by the time we get to the star is going to definitely be in milliarc seconds. And since we need to do the ratio later on, it's going to be best if we've got both of them in the same units. So, so 1/1000th of an arc minute multiplied by 60 multiplied by 1,000 to convert to milliarc seconds. The 1,000s cancel out and we are left with 60 milliarc seconds. Good. So it's probably closer to 50 than it is to 60 because the biggest, other than kind of not knowing where the Earth is and that kind of thing, the biggest approximation that we made is to say that the Sun is 1 million kilometers, not 1.4. But like I said, with a Fermi approximation, we call it a win if we get within 1 order of magnitude, typically. So if it's between 6 and 600 milliarc seconds, then it's a win. Right, so next we are going to do the angular diameter of the star. So we can use the exact same trick, and I'm actually going to use the exact same starting point. We're going to use the fact that the sun is half a degree and 1 AU away, and we're going to use that to come up with an estimate of the angular diameter of the star. So first of all, since I'm pretending that the sun is the same size as the star, we don't have to worry about any changes because of the diameter. We only have to worry about changes because of the distance. So what we're looking at is 30 arc minutes multiplied by 1 AU and divided by 100 light years. So the problem is, how do we convert to a single unit in order to solve this? Well, I think that the simplest way to do it, in the way that I did it in the lecture hall when we were having the lecture, was to basically think about both of these in terms of time. Now, something that a lot of people are taught, so I imagine most people watching this video would know this, is that the light travel time between the sun and the earth is about 8 minutes. And that's sort of a little bit too low. I think it's sort of something more like, I want to say 8 minutes and 20 seconds or something like that. In fact, I've even got 8 minutes 24 seconds in my head. But really, we don't care. We are going to say 8 minutes. So we need to take 30 arc minutes, multiply it by 8 light mins, and then we need to divide by the number of minutes in 100 years. So how many people know off the top of their head how many minutes there are in a year? Okay, I don't, but I happen to know, roughly speaking, how many seconds there are in a year, because that's actually a useful conversion factor to carry around in your head. There are approximately 30 million seconds in a year. It's actually, I think it's 31-ish, but okay, if there are, so 100 years is, we can multiply by 30 million and divide by 60 to get to minutes. So 60 converts, getting rid of the 60 converts this to 500,000. Okay. So now we have them in the same unit. 8 light minutes for the distance to the Sun, 100 times 500,000 light minutes for the distance to the star. Okay. The nice thing to do next is to add in the conversion for converting arc minutes to milli-arc seconds. So if we do that, we say it's 30 times 8 times 60 times 1000 divided by 100 times 500,000. Okay, so we can get rid of these 3 zeros with these 3 zeros. We can get rid of these 2 zeros with this 0 and this 0. And we are left with 3 times 8 times 6 divided by 500. Fine. So 6 eighths of 48, which is as near as damn it 50. So we can then get rid of the 50 and call it 10 by getting rid of 6 times 8. Which means that the angular diameter of the star is approximately 0.3 milli-arc sec. So the real answer is probably closer to 0.2 than to 0.3, but I would be very surprised if it was either less than 0.03 or greater than 3. In fact, it can't be. I know. I was thinking how many stars actually have more than 1 milli-arc second as a diameter. It's not very many, but yeah, Betelgeuse is oh gosh. No, I'd have to go through the same exercise for Betelgeuse, which I'm not going to do now because that would definitely make the video too long. But yeah, I'm not going to guess. Let's carry on. Okay. So the next question is, what is the ratio between these two? So the ratio, according to our estimates, is 60 divided by 0.3, which is 200. So the angular diameter of the asteroid is about 200 times greater than the angular diameter of the star. Now, this is actually the answer that I'm probably going to be most confident in, because I made the same approximation for the asteroid and the star, in the sense that in both cases I was pretending that the Sun was 1 million instead of 1.4 million kilometers in diameter. So in those two approximations cancel out, I'm thinking 200 is going to be very close to the right answer. Okay, so how fast does the asteroid move in the sky, and how long does a possible occultation last? I'm actually going to skip this question and answer this question first, because personally I find it, when I was doing it in the lecture, I found it easier to do it that way around. And you're going to see why in a second. So, how long does a possible occultation last? So we need to start by estimating the length of the asteroid's year. So to do that, we need Kepler's third law. Kepler's third law says that the period of an orbiting object is proportional to, oops, that's not proportional, proportional to the cube of its semi-major axis. Since all orbits are elliptical, it's not, strictly speaking, the radius, but if we pretend that the orbit is circular, then we can use the radius, because the radius is going to be the same as the semi-major axis in the case of a circle. Now, that's probably fair. Other than stuff like comets, most orbits in the solar system are fairly close to circular, and making that assumption is almost certainly not going to change the estimate by more than an order of magnitude. And we don't have any information about the parameters of the asteroid's orbit, so kind of don't have any choice. We may as well assume it's circular. What we need to do is to compare the orbit of the asteroid to the orbit of something where we know what both P and R happen to be, and that's the Earth. It's the obvious choice. So in the case of, for the Earth, P is 1 year, R is 1 AU, pretending that the Earth's orbit is circular. So, asteroid R is 3 AU. So, since we have tripled R, what we can do is we can say that P asteroid is equal to the square root of 3 cubed because of this proportionality. So since r is multiplied by 3, p squared is 3 cubed. So anyway, you get the idea, I'm sure. I could write it out more, but I think that's all you need. So 3 cubed is 27, but let's pretend it's 25, and the square root of 25 is 5, and therefore a year for an object orbiting the Sun at 3 AU is approximately 5 Earth years. Cool. So what I want to do now, what I'm really after here, I should have explained this earlier, but what I'm really after here is kind of like the angular velocity of the asteroid. So the asteroid is going around the Sun in 5 years, then how long does it take to move through a particular angle? And obviously the angle that we're interested in is the angular diameter of the asteroid itself, because if we can work out how much time it takes for the asteroid to move through its own angular diameter, then that is an approximation for the possible length of the occultation. So we want to start by converting 5 years of the orbit into the number of days it takes to move through 1 degree. So how many days to move 1 degree? Okay, there are 365 and a quarter days in a year. There are 360 degrees in a circle. So 5 times 365.25 divided by 360. I'm going to call these the same and cancel them out. So 5 days to move 1 degree. Okay, the next thing I want to do is to convert that to hours, and you'll see why in a second. So 5 times 24 is 120. For 1 degree. Okay. So the reason I've converted it to hours is that makes the next step super easy, because what I want to do next is to convert this from hours for 1 degree to seconds for 1 arc second. And there are 60 minutes in an hour, there are 60 seconds in a minute, there are 60 arc minutes in a degree, and there are 60 arc seconds in an arc minute. So all of those cancel out, and we can say that it will take 120 seconds for 1 arc second. So if it takes 120 seconds for 1 arc second, how many seconds does it take for the angular diameter, which was 60, yeah. So 60 milli-arc seconds. So to get there, we need to take 120, multiply by 60, and divide by 1,000. Which is 12 times 6 divided by 10. Which is 7.2 seconds. So that's the answer for the last question. The Fermi approximation is 7.2. We shouldn't keep the 0.2 because that is precision that we can't justify. So 7 seconds. Since we're probably overestimating the angular diameter of the asteroid, it's probably shorter. It's closer to 6 or even 5 seconds. But again, like I said at the beginning, there's a lot of stuff that we don't know. If the Earth is on the same side as the asteroid, if it's on the same side of the Sun as the asteroid, then the angular diameter is going to be bigger. But actually, as well as that, there's the fact that the Earth is also moving, and it's rotating, and if we wanted to come up with a better estimate, we'd have to take those into account as well. Fine, but I'm not going to do any of that. I'm going to say, in all probability, it's more than 0.7 seconds, and it's less than 70 seconds. I'm guessing that it would still be in that range, even if we took into account the fact that the Earth is also moving. So finally, how fast is it actually moving in terms of like, yeah, not in terms of angles, but in terms of distances. The actual diameter is 100 kilometers. It has moved through its own diameter in 7 seconds. So velocity is 100 over 7. It's as near as it's yeah, it's roughly speaking 14 kilometers per second, because 10 sevens are 70, 4 sevens are 28, so 14 sevens are 98, which is close enough to 100, so it's approximately 14 kilometers per second. In this case, I would keep the second significant figure. So when you get close to 1, you like the second significant figure is more important. I'm not going to explain that here, but it's like the difference between 7 and 7.2 is a lot smaller than the difference between 10 and 14 or 10 and 12. So you kind of like, when the first significant figure is 1, then you're more justified in using a second significant figure. But like the point is, if it's greater than 1.4 and less than 140, then we call that a win. So I'm probably going to make another video talking about why this ratio works, the ratio method of calculating angles works for small angles but not for large ones. Yeah, but for now that's it, and I hope you enjoyed it.